Okay, let's take a look at the geometry, or how to determine the geometry when we have three groups that are around the central atom. I have two examples over here, and I've already tallied the total number of electrons. So let's do the Lewis dot structure for this compound. Remember that I have boron, and boron is that exception that does not need all of the, it doesn't need a full octet around it. But because it's the least one, I have three of these, but only one of these, this will most likely be my central atom. And then the fluorines will be bonded around my boron. And then I have to go around and give the fluorines their lone pairs to make them happy. So they have 8 electrons around. Okay, now let's see. Each fluorine has 2, 4, 6, 8 electrons around. 8 times 3, that gives me 24 electrons. So I've used up all my electrons, but boron is the exception that does not need 8 electrons around it. It has 2, 4, 6 electrons. Now, anytime you have three groups around the central atom, be they atoms or a lone pair and 2 atoms, it doesn't matter. Anytime you have 3 groups, just like that, that gives you an electron pair geometry of trigonal planar. So that means that you have all 3 of these groups, all of them are on the same plane. And if I were to draw a triangle here, the boron would be right in the middle, and these fluorines would be at the edges of the triangle. And each angle here would be 120 degrees, because that is, all of these are equal angles, and they have to be, these 3 angles being equal. So I have 360 degrees now divided by 3 groups gives me 120 degrees angles. Those are the angles that these groups have to be from each other to not repel each other. And that's the furthest away they can be from each other is 120 degrees, because now I have 3 groups instead of 2. So the trigonal planar is the electron pair geometry and the molecular geometry for this one, because they match. I have 3 atoms around that central atom, and I don't have any lone pairs. Now when we get into more than 2 groups around the central atom, we start to see the effect of lone pairs, and that's where the electron pair geometry and the molecular geometry will differ. But in this case, because I have 3 atoms around the central atom, 3 atoms for 3 groups, both the electron pair geometry and the molecular geometry will be the same, will be trigonal planar. Let's look at this example. I have 18 electrons, and my sulfur is the central atom, and it's bonded to my oxygens. Now I'd have to double bond because my oxygens will not be happy. So there we go. We have 2 double bonds. Remember how we talked about oxygen either having 2 single bonds with 2 lone pairs or a double bond with 2 lone pairs. So here's my double bond, and let's give oxygens the 2 lone pairs. And then let's count total electrons. 2, 4, 6, 8, 10, 12, 14, 16. I have 2 more electrons. Oxygens are happy with their octet. Now sulfur is one of those that can accommodate more than 8. So it's got 2, 4, 6, 8, but I have 2 more electrons, and those will go as a lone pair on the sulfur. Note that I have replaced one of these atoms with a lone pair. So now I still have 3 groups because I have 1, I have 2, and this counts as a 3rd group. So I have 3 groups. So my electron pair geometry, which looks at just how many groups do I have around, not the types, but just the number of groups. This is still trigonal planar. However, the molecular geometry, because I've replaced one of those 3 atoms with a lone pair, and the lone pair takes a lot more room than just the atom would, so it kind of pushes these bonds down a little more, meaning the angles now are not going to be quite 120 degrees between the lone pair and those 2 atoms. This makes the molecular geometry to be bent. So that's the distinction. Here I have 3 groups around the central atom, so my electron pair geometry for this molecule is the same as the molecular geometry because I have 3 groups and 3 atoms, no lone pairs. But here, what I've done, I have 3 groups still, so my electron pair geometry is trigonoplanar, but I replaced one of the atoms with a different group, which is a lone pair, and now they're not. The lone pair takes up more space than a regular atom, and therefore the angles are not equal to 120 degrees now, which means that I'm bending this molecule a little more. This is a bent geometry, a bent molecular geometry. I will erase this, and then we will talk about the very last geometry that we will deal with in this class anyway. That will be with 4 groups around the central atom.